Thank you very much, Selena. The title of my presentation is Realistic Modeling of Difficult Land Seismic Noise and Subsequent Testing of Noise Removal Methods. Now, let me review the difference between marine and land seismic data. Now, here on the top, you see a typical marine section. It has good bandwidth, sharp reflections, and you can see a lot of subtle features here, and the faults come out well. Now, in contrast, land seismic data is often poor. You don't have good bandwidth, you don't have good faults, and sometimes you have washout zones where you get almost no image. Now, land seismic data quality can vary dramatically. Sometimes you do get good data, but often you do get bad data. And we're going to focus on the problem data. So why is land seismic data so different than marine? Well, you have strong noise, and it's caused by elastic propagation near the sources and receivers, by the fact that you have ultra slow velocities at the surface. You have shear velocities that often go down to 100 meters per second. And this is well documented that it happens quite a lot. And lastly, you have strong heterogeneity in the near surface. And by the near surface, I mean the top 30 meters. Sometimes people describe the near surface, they mean the top 500 meters. But here we're looking very much at the very near surface. And the effects on the data is that you have much unwanted energy. And I want to caution you, don't call it all surface waves. Surface waves mean some very specific things. And a lot of this unwanted energy is actually not standard academic surface waves. You also can have low signal strength at the reflections. And then you can also have significant distortion of the reflection signal. And this distortion can be more complex than statics or amplitudes. Sometimes you can have 80 or 90% of your reflection signal being distorted that won't stack in well. And this is also a type of noise that's fairly significant. The interesting thing about this type of noise is that if you can undo the distortion, then you can recover more signal in your data. So here I'm going to show you a movie that'll demonstrate some of the complications of the near surface. We have a source here at depth, and then it starts propagating cleanly. You can see there's some vertical layering here. But then when we get to the complex near surface, you have a lot of scattering. And in fact, a lot of energy is trapped and is reverberating even after this wave front passes through. So here we're creating a lot of noise at the receivers, even though we have a source at depth with a clean. So you can get strong distortion at the receivers. And if you had the source in the near surface, that would also, of course, create a lot of noise. So the two most problematic noises with land seismic data are surface scattering and refraction multiples. Now, often they happen together, which causes a problem. We're going to look at them separately, and that's something that modeling lets us do. Note that surface waves are usually not a big problem with modern acquisition and processing. And I think part of the confusion here is that some people refer to surface waves as a broad term as anything that's caused by the near surface, when in reality, in academics, surface waves mean something very specific. It doesn't include these other types of effects. So surface waves, the terminology, I think is just too confusing, and I try to avoid it. Academic surface waves are usually not a big problem. These two, surface scattering and refraction multiples, are usually the big problem. So here are examples of shot gathers from around the world. The first one is from Papua New Guinea, and you can see the refraction multiples here. They're in a way echoes of the first arrival, and the first arrival is actually up here, and these refraction multiples, and you can see, are even stronger. These are P refraction multiples. Here, this is shear refraction multiples, and these are often surprisingly strong. And then here you have a hint of a surface wave. On the right, this is an example from West Texas. Again, you have the P refraction multiples. And the refraction multiples, they're really echoes of the first arrival. The shear refraction multiples are here, and you can see they're strong. They're sometimes confused with surface waves, but the way you can tell that they're shear refraction multiples is that they're first not dispersive, and they actually have about twice the travel time of the P refraction multiples. So they're actually quite fast, much faster than most surface waves. Here's an example from China. Again, you can see all the energy down here. It's lasting for more than a second after the first break arrival. And there's a lot of incoherency in these later arrivals. Here you have the shear refraction multiples. They're stronger. They're often stronger than the P refraction multiples, and they often have a lot of incoherency. Now, there are several things that cause these refraction multiples, several physical processes that cause them. It can be guided waves. It can be actual layering in the near surface. It can also be scattering that causes refraction multiples. In fact, scattering can convert surface waves into refraction multiples. But so there are several things that can cause these. I like to just use the general term of refraction multiples as a larger category of this noise. There really are echoes of the first arrival. So I think refraction multiples is the best term. On the right is an example from Romania. This I actually pulled off the web. Here you can see these later arrivals that are almost perfect echoes of the first break. And then here you can see the shear refraction multiple, and it has a lot of incoherency. So this is actually a major problem with data. So here's synthetic model data, and this focuses on scattering. So you see very little coherency between neighboring traces. And here we actually have 5 meter spacing, so fairly small spacing between receivers. There are some refraction multiples here and here, but they're really not that strong. And there is a strong reflector down at the bottom. But you can see in general, there's a lot of incoherency between traces, and you have hints of reflections here and here, but just the incoherency makes them, well, fairly weak. And you also have some surface waves here that are also fairly weak, but just not very significant. So here is synthetic model data, and now we're focusing on refraction multiples. There is significant coherency between neighboring traces, but you can see the refraction multiples here are now much stronger, and they last for a long time after the first arrival. And the shear refraction multiples here are much larger amplitude, and in fact, they're stronger than the P refraction multiples. And again, we have some weak surface waves. Here again is the previous slide with the scattering. The refraction multiples are not as strong, but you have a lot of incoherency between neighboring traces. And then here again is the synthetic data that focuses more on refraction multiples. Notice that there's much irregularity with the refraction multiples. And this is a problem because means you can't remove them with standard velocity filters like a linear radon. You might remove half of them, and that's good, but we actually want to do better than that. So the benefits of modeling is we can understand the physics better. We can test and understand existing processing capabilities, especially when we have an idea of the answer. We can develop new methods when data does not have other complications, and we can test different acquisition approaches. And I'm going to do all four. I've already shown you some of the physics of the noise. And I'm going to show you three types of data. One is acoustic with no surface variations and no refraction multiples. And this is a simple control. This might be similar to a marine case. I'll then show the acoustic data with surface variations, and this has a few challenges. And lastly, I'll show you the elastic data with surface variations, and this is surprisingly difficult. It's much more difficult than the acoustic case. So here is the p-velocity model that I'll be using, and it's mostly simple layer case except for the very near surface here. You can see the top 30 meters, which is the red and yellow layer up here, contains some heterogeneities, but usually this data is pretty uniform. So time processing should work in this case, and that's on purpose. We want to avoid any complications from depth migration. Here is the density model, and this is much more complex. And the reason for this is this lets us create complex reflections without making the velocity model more difficult. And we have several different steep dips and some subtle features here in the model, which you'll see better later on. So the 2D acquisition we have here are 401 shots with 20-meter spacing. That's an 8,000 meter shot range. We have a receiver spread of minus 4,000 meters to plus 4,000 meters with a spacing of 5 meters. This is fairly tight spacing, and this helps in some cases. I think modern acquisition is moving to tighter receiver spacing, but also I don't want these results to be people to say, oh, you could have just solved this with tighter receiver spacing. You'll see tighter receiver spacing doesn't really fully solve this, even with the 5 meter spacing. So the fold here is 800 with 10-meter common midpoint bins and frequencies of 4 to 55 hertz. So here is the pre-stack time migration image result for the acoustic data with no surface variations and no refraction multiples. So this is like the marine imaging. And the image is very good. All steep dips and subtle features of the model is well imaged. And there are no refraction multiples, no interbed multiples in the data. And so you can see this is what we hope to produce with the more complicated cases. And here is the result of the migration of the acoustic data with refraction multiples. And here I'm doing conventional processing with the strong radon. And the deeper part of the model is pretty well imaged, but the shallow part of the model is more poorly imaged, and that's because the refraction multiples mostly corrupt the shallower reflections. We don't really have the shear refraction multiples in this case that corrupts the deeper data. I do want to mention, as part of the conventional processing, we actually have pretty good statics here. So before I go to the elastic data with surface variations, let me point out that with the elastic data, the refraction multiples are stronger. The shear refraction multiples exist. They're strong and they harm the deeper reflections. And we also have more irregularity and incoherency between neighboring traces in the pre-stack data. So here's the elastic image result, and it's a lousy image. There's almost nothing is resolved. You have a few faint reflections here and here. These are the strongest reflections in the model. In this case, we used good statics and velocities, but no radon. Now let's include radon in the processing. And you can see the image is significantly better. It's not great, but now you can see more of the reflections here and here, and down deeper. Still not a great image, and this is what we like to improve on. Here, I've redone the same processing, but with 1 meter receiver spacing. And you can see the image is not much improved at all. So in this case, better inline sampling is not the answer, and it doesn't help. I think better cross-line sampling would help, but since this is 2D data, we can't really test that here. And here we go back to the 5 meter spacing data, and we use some advanced coherent noise removal. And you can see the image is better, but the faults are still weak. You have some hints of faults here and here. And the bottom reflections are a little bit better resolved. There's still lots of room for improvement. I just computing this synthetic data for a week, so I've only had a week to work with this, and I've only run it through some of our standard flows. But this is realistic data. So now let's look at some more stronger scattering. And here is a road cut, and you can see the top 5 meters of the Earth, and you can see it's very heterogeneous with a lot of boulders. And the boulders, they're only a meter or two in size, but the surrounding rock is very slow. Remember, you have shear velocities as low as 100 meters per second. So your wavelengths are down in the 1 or 2 meter range. And you have a lot of crosstalk between shear and P energy. So this messy near surface causes a lot of scattering. Now, this small scale, the messy near surface is actually really difficult to model with realistic land seismic noise. Much complex physics happens in those top 5 meters, not to mention the top 30 meters, and elastic wave propagation plays a big role. You get a lot of conversion. And it's very computationally expensive. You need a small grid spacing of about 1/2 meter, and you have velocities down to 100 meters per second. And just my creating realistic models of scattering and refraction multiples took a while. It took about 20 iterations. So here I'm starting with 2D modeling, and we do hope to move to 3D eventually. So here is the surface velocity model to simulate scattering. And you notice the scale here is we're looking at the very near surface. Most of the scattering is in the top 10 meters with some heterogeneities in the top 20 meters. And the heterogeneities are size 1 to 2 meters. And this creates the synthetic data that I showed you before. There's a little incoherency between neighboring traces, poor signal to noise. The refraction multiples are there, but they're not that strong. And you have hints of reflections here and here. So with this data, I'm going to try actually 5 different acquisition approaches, and all have shot spacing of 20 meters. I'm going to first try regular spacing with 20-meter interval. And you can see the blue dots here kind of symbolize the receiver spacing. This produces fold of 100 for this data. I'm going to try regular receiver spacing with 5-meter interval. And you can see the blue spacing here. This produces fold of about 400. I'm going to use digital arrays So each array here contains 10 receivers with 1 meter spacing, and the distance between the array centers is 50 meters. The overall average spacing is 5 meters. So number 2, 3, and 4 have the same number of trace density with just different geometry. And number 4 is dithered or irregular receiver spacing, so that the overall spacing is 5 meters. And then here you see the example of what the dithered spacing looks like. And finally, for number 5, I'm going to try regular spacing with 1 meter receiver interval. And these are the 5 results. This is the elastic data with scattering for 5 different acquisition geometries. Now here we just had perfectly flat reflectors, and the best thing to look at is the far right, where we had 1 meter receiver spacing and fold of 2000. This is close to the correct answer. You can see the flat reflections. You can see where the reflections should be. In this case, the very dense receiver spacing helped a lot. Now in the middle 3 cases, with similar folds, you can see they're about similar signal quality. And on the far left, with 20 meter receiver spacing, well, the image quality is worse. An interesting thing in the middle 3 is that there's actually, I found surprising how different they are from each other. Even though we use similar processing on all of them, and they all, but I think this shows some of the inconsistency or instability of land seismic processing when coupled with aggressive noise removal methods, which we need to do. If we do more enhanced processing, and this involves more complete surface corrections, you can see the results are now all improved. The right side is nearly perfect, and the 3 middles are all pretty good and much more similar to each other. And the left, with the 20 meter receiver spacing and lower folds, you can see now the reflections are actually somewhat well resolved. We still have lower signal to noise ratio, but we're getting a reasonable image. So in conclusion, high fold and statistical noise removal does not solve all problems. It can help, especially for scattering noise, not necessarily for refraction multiples. And enhanced processing can help. And second, dense inline acquisition will help scattering noise, but not refraction multiples. But overall, I think you can see that modeling and testing can help individual projects. It helps you understand your noise and helps you understand how processing can help. Processing a different acquisition can help or hurt your the type of noise you have. And I kind of wonder, has land processing stagnated? We really haven't seen much improvements in the last 10 years, say after 5D interpolation. And I consider compressive sensing to be just a version of 5D interpolation. And can we value and motivate improved processing for the difficult situations of scattering noise and refraction multiples? Can industry benefit from tests of processing using standardized, realistic synthetic land data? And these tests can significantly help technology development and, well, defining the problem is often 70% of solving it. But public tests are expensive and risky for processing companies, and land processing actually has, well, is a difficult business to be in, let me tell you that. Processing margins are already thin, and asking land shops to do public tests for free is not a great idea. And also, how can we recover the costs of producing the synthetic data? We've already put a lot of time and effort into this. Should oil companies pay for their preferred vendors to perform tests? And can these tests encourage companies to identify and value quality and to not necessarily use the lowest bidder? That concludes my talk, and I'm very much interested in feedback. Thank you very much.